This is a continuation of Stewart Notes 2-7, Part 2. To finish what we started before, we were taking a look at position, and the derivative of position is velocity. And one thing that we need to talk about is speed. And speed is defined to be the absolute value of velocity. So if you find the velocity, take its absolute value, and that will be the speed, which makes sense if you think about you drivers. When you take a look at that instrument in your car, it's called a speedometer, which means that it's telling you how fast you're going, but there are no negative or positive values. It's all positive. All right, let's take a look at finding the derivative of a more complex function. This is a trinomial, and we're going to go back to the definition, the a plus h, and we want to find it at the number a, which is, it could be any number in the domain for the function. And notice you substitute in, and you will have to expand and simplify, and in the end you are going to get a formula right here. This is a formula for finding the slope of the instantaneous rate of change, and as long as you give me an x value or an a value, I'll be able to find it. So what's the advantage of finding a derivative at any point a, like what we were just talked about? And the advantage is that you can have different points and find the instantaneous rate of change without going back through the derivation again. So for this particular problem, if I want to find the equation of the tangent line, remember an equation of a tangent line requires 1, the slope at 3, and which is the slope, and 2, you're required to have your point, and of course the point is 3, -6. Now we do have a formula for finding the derivative at 3, so all we have to do is put 3 in for a, and we'll get -2. So this slope will be -2. We can write our equation, y plus 6 is equal to -2 times the quantity x minus 3. And you can leave it in point slope form. That is fine. That's the equation. Okay, so instantaneous rate of change is the limit of this slope idea as the denominator gets closer and closer to 0. And we can write it this way with a 2 points version here. And this is our notation that we use. And we call this instantaneous rate of change at a point A. Let's take a look at how we utilize derivatives in economics. A manufacturer produces bolts of fabric with a fixed width. The cost of producing X yards of this fabric is C, which equals F of X dollars. What's the meaning of the derivative? Okay, so F prime of X will be equal to the change in C over the change in X. Now, what does C represent? C represents dollars. And what does X represent? X represents, you can see right here, yards. So let's take a look at the answer. And we can see that that's what we got, dollars per yard. Economists call this marginal cost. Now the next problem says, in practical terms, what does it mean to say that f prime of 1,000 equals 9? All right, and remember we have decided that the units is going to be dollars, so this will be $9 per yard. So what does that really mean? Well, it means that if you take a look at this rate of change here, and remember, if you let this is an approximation, so this slope of the secant line is approximately equal to the instantaneous rate of change. And if you let this small denominator be 1, 1's pretty small when you're thinking about going to 1,000, you are going to get that this rate of change is approximately equal to delta C. So, which tells you that the next yard is going to cost $9. So that's what that means. The next yard, the 101st yard, will be $9. Now, which do you think is greater? F prime of 50, F prime of 500, F prime of 5,000. Now, 50 means after 50 yards of manufacturing. This means 500 yards of manufacturing, 5,000 yards of manufacturing. So let's take a look at what we think is greater. Well, they say that F prime of 50 will be greater than F prime of 500. In other words, this is the startup when you first start manufacturing the fabric, and it costs more. And if you make more and more, it's more efficient, and the use of the fixed cost of the productions, and you start making money. It kind of sounds familiar. But once you get to 5,000, can you really get up to 5,000? And it's good operation. And chances are with these large operations, they become inefficient, and there's sometimes overtime costs and things like that. So there's a point at which making more and more isn't really feasible or economical. And this is the end of the screencast.